Okay, so let's talk about MR physics in introduction. And I guess, okay, so I'll go like this. Okay, so there's a lot of things to discuss in this first lecture. We're going to talk about something called the electromagnetic spectrum. We're going to talk about something called B0, the external magnetic field. We'll review a little bit of high school physics when we talk about protons. We'll talk about a quantum mechanical property that protons have called spin. We'll talk a little bit about a physical property that protons have by virtue of their spin, so-called magnetic dipole moments. These magnetic dipole moments in the individual protons impart, when we do our MRI imaging, a magnetic field in the patient, which is called M0. So M0 is the magnetic field in the patient, not to be confused with B0, which is the external magnetic field. In addition to having a quantum mechanical property called spin, protons have a physical property in certain situations called precession. The precession occurs at a particular frequency, which is governed by something called the Larmor equation, which we'll talk about in the gyromagnetic ratio. In addition to protons having spin and magnetic dipole moments and precession, under certain situations, protons will relax. And there's two kinds of relaxation we'll talk about today. There's T1 relaxation and there's T2 relaxation. In order to make use of T1 and T2 relaxation to create MR images, we will talk a little bit about radio frequency excitation. In addition, we'll talk a little bit about loss of coherence or dephasing, and we'll end with something called chemical shift. So a lot to talk about in this first lecture. Let's start with the electromagnetic spectrum. Well, actually, before we start with that, let's just do a quick introduction, a quick overview of MRI. So in MRI, we start with a very large, powerful magnet. And then into this very powerful magnet, we put a person. You don't have to put a person. You could put a phantom in there. You could put a bottle of water. You could put anything you want in there. But we typically put people in there for clinical MRI. And then we're going to send radio frequency energy into this patient or this sample or whatever we put in there. And then the patient will then send radio frequency energy back at us, and we will listen to that energy that they sent back to us. And from that energy that we listen to, we will construct an image. Now, we were talking about radio frequency energy. So where is radio frequency energy in the spectrum of the electromagnetic spectrum? So this is just a little bit of a reminder from high school physics. The electromagnetic spectrum can be described in terms of the frequency of the waves, or in terms of the wavelength of the waves. Notice that as the frequency goes up, the wavelength goes down. So at the very top, we have very, very short wavelengths, 10 to the minus 10 centimeters. And at the other extreme, we have long wavelengths, 10 to the 5 centimeters. Notice that the energy is proportional to the frequency. So the highest energy is way up here where the frequency is high. As the frequency goes down, the energy goes down. Okay, so high energy electromagnetic energy is X-rays. So X-rays have a wavelength of about 10 to the minus 9, 10 to the minus 8 centimeters, very high energy. Ultraviolet light is a little bit less energetic and has slightly longer wavelengths, 10 to the minus 6 centimeters. Visible light, slightly less energetic, slightly longer wavelengths. Infrared energy, even lower energy, slightly longer wavelengths. Then we get to microwaves. Notice that microwaves have a wavelength of around 10 to the 0 centimeters, so about 1 centimeter, or maybe about 1/10 of a centimeter, 10 to the minus 1. Finally, we get to radio waves and TV, and so this is sort of where we are when we're talking about MRI. So MRI is in the radio frequency spectrum as indicated here. Now, another way of looking at the same thing is let's now look at this radio frequency spectrum, which goes from about 1 megahertz to about 100, well, to about 200 or 300 megahertz. And if we look at AM radio is on the order of about 1 megahertz. And let's look at FM radio. FM radio is about 88 to 108 megahertz, so that's where radio stations are. Now, what about MRI? Well, sorry, before we get to MRI, let's talk about TV channel 2. So TV channel 2 is at about 64 megahertz, and it turns out that's where MRI is at 1.5 T. So MRI at 1.5 Tesla is operating at the radio frequency of TV channel 2. Now, MRI at 3T is twice as much. So what's twice of 64? Well, about 128. So that's where MRI at 3T is. And it turns out that MRI at 3T is at around the same frequency as air traffic control. So we know that with MRI, we need to shield the radio frequency from the external environment. And one reason we want to shield the MRI from the external environment is so that the external environment doesn't inadvertently talk to the patient in the scanner by interfering with the radio frequency pulses. But another reason we want to shield MRI is that we don't want the radio frequency of the MRI to get out into the air, because you can imagine that if we're scanning someone at 3 Tesla, there's an airplane going over, in that area, our signals might interfere with air traffic control. Okay, so 3 Tesla is air traffic control, 1.5 Tesla is TV channel 2. Now, I mentioned that we put patients into an external magnetic field, and this external magnetic field is described by something known as B0. So that's the strength of the external magnetic field. And when we do clinical imaging in the year 2018, we're typically using a 1.5 T or a 3T magnet, as indicated here. And as an order of magnitude, these magnets cost about $1 million. Now, just by comparison, the industrial magnet that can pick up your car is weaker than the magnets that we have for clinical care. So these magnets are only 0.3 Tesla. They're a lot cheaper too. They're only about $10,000. So you might choose which kind of magnet you want to buy. But at any rate, the industrial magnets are weaker than the magnets we use for clinical care. Now, I made this lecture originally about 12 or 13 years ago. And back then, the Earth had a magnetic field of 0.00005 Tesla. I don't think that's changed in the last 15 years. But you can see now that the magnetic field of the Earth is much weaker than the magnetic field of a magnet or the magnetic field of the kind of thing that can pick up your car. And 15 years ago, I made a back-of-the-envelope calculation that the Earth was worth $10 to the $17. That may have changed in the last 15 years. I have not redone that calculation. Now, when I first made my lecture, this was my son, and he was reaching out for a little magnet that you kind of put on your refrigerator. And as an order of magnitude, those cost about $1, probably more like 10 cents. And the field strength of those is about 0.01 Tesla, so much weaker than a clinical MRI. Now, this is my son now. So you can see that on his knees, he is much taller than he was, 13 or 14 years ago. And I think that magnets might be more expensive now too, I'm not sure. Okay, anyway, so now another question is, okay, so we know that these clinical scanners have very strong magnetic field, but how strong is 1.5 or 3 Tesla? Well, I unfortunately know exactly how strong a 1.5 Tesla scanner is, because in 1994 or 1995, before I got into the radiology residency program at UCSD, I was doing research in MRI. And in the 1990s, things were more relaxed now. So you could actually, without having essentially any training or any credentials, you could bring a human being into a scanner and scan the patient. And so that's what I did. I was doing orthopedic research, and I brought a patient into the scanner for research. This particular patient was in a wheelchair. So I left the wheelchair by the side of the room, and then I got the patient, and I helped the patient start to get onto the table. As then I'm walking with this patient, with the patient's arm sort of leaning on me. Suddenly I hear this noise, and I see this wheelchair moving, and it's going faster and faster and faster. And it gets sucked into the scanner at probably, 30, 40 miles an hour. Now, I'm thinking, okay, there goes my career. I haven't even started yet, and I've ruined this $1.5 or $2 million scanner. And just like the mother whose baby is trapped underneath the car, they somehow get the adrenaline to pick up that car. I had that same adrenaline, and with all of my strength, I was literally horizontal trying to pull this thing. I was in the air, horizontal, trying to pull this thing out. And I finally was able to extract this wheelchair from the scanner. But it took the adrenaline that it takes a mom to pick up a car for me to get this wheelchair out of this scanner. So these scanners are very powerful. They're really, really powerful. 1.5T3, and that's 1.5T. If it had been a 3T scanner, there's no way I could have done it. So just be aware that these scanners are very powerful, and be aware that something as large as the wheelchair can become a projectile. So if something as large as a wheelchair can become a projectile, you can imagine that something smaller that's metallic or ferromagnetic could, be a projectile as well. And people occasionally, not commonly, but there's occasional deaths of human beings because there's a projectile in the room that just by bad luck happens to hit someone in the body or in the head. So be very careful with this, okay? Very strong magnets. Now, the units of magnetic field strength are named after Nikola Tesla on your left and Carl Gauss on your right. 1 Tesla is typically, Tesla is usually the unit we use for clinical MRI. Be aware that you can also use the unit of Gauss. 1 Tesla equals 10,000 Gauss. So 1 Tesla is a lot larger than a Gauss. Okay, so that's a little bit about B0. Now, why is B0 important other than the fact that it can ruin your radiology career before you start it? So why is B0 important? B0 is important because B0 is what magnetizes the patient, which is essential for MR signal. So we need to magnetize the patient to generate MR signal. B0, and then a lot of things that are important are proportional to B0. So the signal to noise ratio is proportional to B0. All other things being equal, when you go from a 1.5T to a 3T scanner, your signal to noise doubles. That's assuming everything else can be kept constant, which for reasons that are too complicated for today is not always the case. Another thing that's proportional to B0 is artifact to noise ratio. So you can think of artifacts as signals you don't want. So if the signal to noise ratio is proportional to B0, the artifact to noise ratio is proportional to B0. So as a practical thing, what does that tell you? It tells you that when you go from a 1.5T magnet to a 3T magnet, expect to have higher SNR, but also expect to see more and more severe artifacts. Proportional to B0 is also the precession frequency, and we'll see later why that's important. Proportion to B0 is chemical shift. We won't talk about that so much today. Proportional to B0 is something known as susceptibility. We won't talk too much about that either, but just be aware that susceptibility is sometimes something good and sometimes bad. So if you want to be sensitive to susceptibility, you might want to use higher field strength. If you don't want to be sensitive to susceptibility, you might want to have a lower field strength. And then there are things that are related to B0, but not quite so neatly proportional. And those include something known as B1 heterogeneity, which I probably won't talk about too much today, and T1 and T2 star, which are also related to B0. And I won't talk too much about those either as they relate to B0. We'll talk more about these things here. Okay, so that's why B0 is important. Now let's talk a little bit about this quantum mechanical property that protons have. So protons have a quantum mechanical property called spin. And I didn't make this up, but because they have a quantum mechanical property called spin, in the MR literature, people often refer to protons as spins. So whenever you hear someone talk about spins in the setting of MRI, they're talking about protons. So protons have spin, and they don't literally spin, okay, but we can sort of think of them as spinning as illustrated in this cartoon here around an equator. And the spin can either be clockwise or counterclockwise. It can either be positive 1/2 or minus 1/2. The magnitude of the spin is always 1/2, and that's a quantum mechanical derivation. Now, importantly, because the spins, because of spin, this spin induces a magnetic field. And the true explanation is quantum mechanical, but for us who don't understand quantum mechanics, we can just sort of think of the following. anytime you have something that has a charge and that charge is moving, that charge induces a magnetic field. So protons have a positive charge. If protons are spinning, that induces a magnetic field. The real explanation is not that, okay? But in my own brain, I sort of think about it that way. Now, it would be nice if we could just simply say that protons have spin, spins induce a magnetic field, and we could just call it the induced magnetic field, but that would be too simple. So instead we call it the magnetic dipole moment. Now, I am the messenger. I did not invent this terminology, but just be aware that the quantum mechanical property called spin creates or induces a magnetic field. That magnetic field is known as the magnetic dipole moment. Because of this magnetic dipole moment, we can think of protons or spins as being bar magnets that have a north pole and a south pole with magnetic field lines as illustrated on this slide over here. Now, the spin direction, positive 1/2 or minus 1/2, determines the direction of the magnetic dipole moment. So if the spin is positive 1/2 or minus 1/2, the magnetic dipole moment will either point up or will point down, respectively. So far, so good. Now, why is that important? Why is it important that we can have either a magnetic dipole moment pointing up or a magnetic dipole moment pointing down? Well, the reason it's important is that paired protons will cancel out. So look at the proton on your left. There's a single proton, a single spin, and the magnetic dipole moment in this particular case is pointing up, which means that there's a magnetic field that points up. Now let's look at the nucleus on the right, in which we have paired protons. Now, by random chance, one proton on average will be pointing up, and by random chance, on average, its companion will be pointing down. And notice now that the magnetic dipole moment from one proton cancels out the magnetic dipole moment of the other. So if you looked at the entire nucleus as a whole and asked what's the magnetic dipole moment of that nucleus, you'd say it's 0 because of cancellation. So paired protons cancel out. What this means is that nuclei with an odd number of protons have a net magnetic dipole moment. So that makes sense, right? Because if you have an odd number of protons, then on average, one of them will be pointing either up or down, and you end up with a net magnetic dipole moment. Now, what I don't understand, I fully confess I do not understand this, is that in addition to an odd number of protons, nuclei with an odd number of neutrons also have a magnetic dipole moment. Now, that's the part I don't really understand, because neutrons have no charge. So I don't really understand why a neutron with no charge induces a magnetic dipole moment. But if anyone can figure that out and explain it to me, then maybe next year, if there is a next year, then I can explain that as well. At any rate, what are the nuclei that have magnetic dipole moments? There's hydrogen, there's fluorine-19, there's sodium-23, there's carbon-13, and there's oxygen-17. And these nuclei have their own spin numbers. You can see that hydrogen and fluorine, for example, has spin numbers of positive 1/2. The other nuclei here have slightly different spin numbers. Now, I don't know why, for example, oxygen-17 has a spin number of 5/2 and hydrogen has a spin number of 1/2. So that goes over my head. But these are the nuclei that have magnetic dipole moments, which means in principle, we could use any of these nuclei for MR imaging. So which nuclei do we pick for clinical MRI in the year 2018? We almost always pick hydrogen. So some of you might be wondering, well, why do we pick hydrogen? Why don't we image fluorine? Why don't we image sodium-23? We can, so why don't we? Well, the reason that we pick hydrogen protons is that hydrogen protons are the most abundant. And to illustrate that, here's the relative abundancy of different protons. So if we assume that hydrogen has a relative abundance of 100%, the next most abundant one would be sodium-23. And notice what this is. This is 0.09%. So this is not 9%. It's not 0.9%. It's 0.09%. And that's the second most abundant one. Look at the abundance of 19 fluorine. It's there's so little of it that it'd be very difficult to actually generate an MR image if we were trying to image a human being based on things other than hydrogen. So we image hydrogen because it's far and away the most abundant. The next question you might ask is, well, what hydrogen protons? Because hydrogen protons are in collagen, they're in other proteins, they're in bone, they're in cartilage, they're in all sorts of substances. They're in proteins and enzymes. So which hydrogen protons? It turns out that for clinical MRI, we look at two types of hydrogens. We look at the hydrogens in water, and we look at the hydrogens in fat. And we can think of MR imaging as a water image and a fat image, and the water image and the fat image are superimposed. So when we do clinical MRI, we are doing a water fat image with the two separate images superimposed. Other protons are essentially invisible using clinical MRI techniques. Amino acids, proteins, cholesterols, other macromolecules, invisible using MRI. So if you wanted to look at proteins with MRI, you can't do it with regular clinical sequences. You have to play certain tricks which are beyond the scope of today's discussion. So clinical MRI, we're looking at water, we're looking at fat. Okay, so now let's look at this very unhappy person and try to figure out, why is this person so unhappy? The reason this person is so unhappy is this person has a lot of protons in their body. And as I mentioned earlier, all the protons have a magnetic dipole moment, but these magnetic dipole moments are all pointing in different directions just by random chance. Let's see if we can make this person happier. Oh, so here they are. You can see that all these protons are just sort of spinning randomly, and they're not in phase with each other. They're not coherent. The person's very unhappy. So let's put this person now into a large magnetic field. And when we put this person in a large magnetic field, we can see that now they become very happy. And why do they become so happy when they're inside a scanner? Because when you put someone inside a strong magnetic field, instantaneously, all of these magnetic dipole moments will either line up with or against the magnetic field. Now, initially, exactly half align with and exactly half line up against the magnetic field. And so, at least initially, the patient has no internal magnetism because either the protons are pointing up or they're pointing down. But something else happens. In addition to lining up with the magnetic field, the magnetic dipole moments start to precess around B0, which, as best as I could animate it, looks kind of like this, but this is sort of the wobbling precession of a top. Okay, so these are precessing. So the external magnetic field causes the protons to align either with or against, and it also causes the magnetic dipole moments associated with those protons to precess. So here I am illustrating spin here and precession here. So the protons have spin. The spin induces a magnetic dipole moment. The magnetic dipole moment precesses. And then you might ask, well, what frequency do they precess at? And that's governed by the so-called Larmor equation. And the precessional frequency is equal to this gyromagnetic ratio times the external magnetic field. For protons, the gyromagnetic ratio is 42.6 megahertz per Tesla. So if you're imaging at 1 Tesla, what's the precession frequency? 42.58 megahertz. What about 1.5 Tesla? Well, you simply have to multiply 1.5 by 42.58, and whatever that is, it's something like 63 something. That's the precession frequency at 1.5 T. What's the precession frequency at 3T? Well, you just take 3 times 42.58, and that's the precession frequency at 3T. So I won't do this exercise for every magnetic field there is in the human universe, but now you understand that all you got to do is you take your magnetic field strength, you multiply by the gyromagnetic ratio, and that's the precessional frequency. In fact, here are 4 different magnetic field strengths, and here are 4 different precession frequencies. And basically what this means is that if you want to do MRI at 1.5 Tesla, you're going to be using radio frequency waves of about 63.87 megahertz. And if you want to do MRI at 3 Tesla, you're going to do radio frequency of about 127.73, because that's the precession frequency of the protons at that field strength. Now, why is this precession frequency important? Because for any given magnetic field, so each nucleus has a different gyromagnetic ratio, which means that for a given field strength, each nucleus has a unique precession frequency. So just to illustrate that, here are the gyromagnetic ratios of those 5 nuclei we talked about earlier. Hydrogen, 42.6, fluorine, 40, sodium, 11.3, etc. So what does this mean? Well, if we're at 1.5, let's just pretend we're at 1 Tesla. If we're at 1 Tesla and we want to do hydrogen imaging, which is what we do clinically, we will use radio frequency pulses of 42.6 megahertz. What if we wanted to do fluorine-19 imaging? If we want to do fluorine-19 imaging at 1 Tesla, we would not use 42.6 megahertz. We would use 40.0 megahertz. So that's why it's important. The fact that different nuclei have different gyromagnetic ratios means that we can select which nucleus we want to image with MRI. Again, which nucleus do we typically use? We typically pick hydrogen because it's the most abundant, but if you wanted to pick a different nucleus, you could. You just have to use the proper frequency based on that nucleus's gyromagnetic ratio. Okay, now spin versus precession, they kind of sound the same, but they're not. So spin is a quantum mechanical property. The protons do not literally spin, but the spin is important because it's what induces this magnetic dipole moment. When placed in an external magnetic field, the magnetic dipole moments of hydrogen literally precess. So precession is a literal physical phenomenon. Spin is a quantum mechanical property. The spin is a property of the proton. The precession is a property of the magnetic dipole moments associated with those protons. Okay, so let's go back to this very happy person whose protons are lined up with or against the magnetic field. And as I mentioned initially, it's exactly half with and exactly half against. But over time, a small number of protons start to line up with the magnetic field as opposed to oppose the magnetic field, as illustrated here. And the question now becomes, why does that happen? Oh, but before we talk about why it happens, let me just explain that if we allow this patient to be in that magnetic field for an infinite amount of time, after an infinite amount of time, we will have a net alignment of 3.4 protons per million per Tesla. So what does that mean? That means that if you put someone in a 1 Tesla magnet, then eventually, for every 1 million protons they have, there'll be 3.4 protons of net alignment. Or another way of looking at this is that there will be 500,000 and 1.7 protons pointing up, and there'll be 499,998.3, I think, if I did my arithmetic correctly, pointing down, okay? But because a slightly greater number of protons are pointing up than pointing down, now the patient is magnetized. So when you put someone in a magnetic field, the patient actually becomes a magnet. Now, they're not as strong as the external magnetic field. They're a very weak little puny magnet inside a strong magnet. Why do more protons align with than against? Because if you think about it, the protons that are pointing against the magnetic field are in a high energy state. So if we have half the protons in a high energy state and exactly half the protons in a low energy state, this system is not in equilibrium. The system becomes in equilibrium when just a small number of protons shift from high energy to low energy. And so the equilibrium is achieved when just the right number are in the low energy state and a slightly lower number are in the high energy state, and now we've reached equilibrium. Now, we could say, as the protons go from high energy to low energy, what happens to that energy? Well, the energy is released. The energy is released to the external environment, which in the setting of MR physics is known as the lattice. So energy is released to the lattice from the spins. So this is sometimes called spin lattice relaxation, because the spins are releasing energy to the lattice. So showing again the same thing, we start in disequilibrium on the left. We then go to equilibrium on the right. And this does not occur instantaneously. This takes a little bit of time to occur, and that time is governed by something known as T1 relaxation. So T1 relaxation is the process of spins going from high energy disequilibrium to an equilibrium state. And because energy is released to the lattice, this is sometimes known as spin lattice relaxation. It's also known as T1 relaxation. Now, T1 relaxation is not instantaneous. It takes a certain amount of time, and it follows an asymptotic growth curve known as a T1 growth curve. So this is the equation for T1 relaxation. It's an exponential curve or an exponential equation that basically tells you that after an infinite amount of time, if you start with a net magnetization of 0, after an infinite amount of time, you will reach a net magnetization of M0, which is your equilibrium magnetization. So after an infinite amount of time, you get to M0, and the way you get from 0 to M0 is governed by this exponential 1 minus little e to the minus t divided by T1. So T1 relaxation is described by a T1 time constant, and when you put the equation in this form, the T1 time constant is in the denominator. Now, if you think about it, anytime you have a time to do something, you might have a rate associated with it. So another way of describing this equation is, instead of having a time constant T1 in the denominator, you can have a rate constant in the numerator. So be aware that T1 and R1 are reciprocals of one another. This is a time constant. This is a rate constant. When you put the time constant, it goes in the denominator. When you have a rate constant, it goes in the numerator. Now, for some of you who are like me, who are a little bit mathematically challenged, we look at equations like this and we kind of get blurry-eyed. But you can take this equation and put it into Excel. And if you put it into Excel and you plug in 0 here, okay, then after a time of 0 and you plug in this equation, you get 0. So you start out with 0. After 1 T1 time constant, you get 0.632. After 2 T1 time constants, you get 0.865. After 3 T1 time constants, 0.950, etc. Another way of looking at this is saying this. You're trying to go from 0 to 1 after an infinite amount of time. With every time constant, you get 63% closer from where you are to where you're going. So if you start out at 0, after 1 time constant, you get 63% of the way there. Once you're 63% of the way there, you now have 37% of the way to go. What is 63% of 37%? Well, it turns out that's about 22%. So after 2 T1s, you're at 63 plus 22%, you're at 86.5. Once you get to 86.5, you're now about 13.5% of the way to here. What's 63% of 13.5? Turns out it's about 9. So you add 9% to this and you get to 0.950, etc. So let's look at this like this. So here we have a graph where I'm going to plot the magnetic field as a time, as a function of t, and on the x-axis I have number of T1 times that have elapsed. So 1, 2, 3, 4, 5. Now I start out at 0, so I'm going to start out over here. And I'm going to go, after an infinite amount of time, I'm going to get to m naught, which is equilibrium. So after an infinite amount of time, I will be at that dotted line. But I'm going to start out here at 0. After one t1 time constant, I'm going to be 63% of the way from 0 to m naught, and it follows an exponential that looks like this. I've now reached 63%. I've got 37% to go. In the next t1 time constant, I'm going to go 63% of what's left over, and that's going to bring me to 86%. I now have 14% of the way to go. In the next t1 time constant, I'm going to do 63% of 14%, and that's going to take me to here, and so on and so forth. Now, for those of you who didn't want to memorize, well, for those of you who didn't follow completely what I was saying, at least memorize the following. Notice that after 3 t1 time constants, you're 95% of the way of your total relaxation. After 4 t1 time constants, you're 98% of the way there. So notice that by the time you get to 3 or 4 t1 time constants, waiting longer doesn't buy you very much. Another way of looking at this is the following. Water has a t1 of about 4 seconds. So if you do an MRI sequence with a TR of 16 seconds, then you would expect water to be 98% relaxed. Would you gain much more signal if instead of doing a TR of 16 seconds, you did a TR of 5 minutes? The answer is no, right? You're already at 98%. All that extra time is just going to buy you 1 or 2% more. It's not worth the effort. Now, different tissues have different T1 relaxation times, as illustrated over here. And you don't necessarily have to memorize this for today, but the concept that I do want you to memorize is that because different tissues have different T1 time constants, if we manipulate the sequence in such a way that we can see the difference in T1s, we can separate tissues on MRI. And actually, there is something I want you to memorize. I want you to memorize that fat has the shortest T1 of any normal soft tissue, and water has the longest T1 of any normal abundant biological substance. Okay, let's talk about net alignment again. So I mentioned earlier that the net alignment is 3.4 protons per million per Tesla. So that means that if you're at 1 Tesla, for every 1 million protons pointing up, you have 999,996.6 pointing down. That's a very puny difference. So given the fact that there's such a puny difference between the protons pointing up and the protons pointing down, how is it that we can generate any signal from MRI? Well, this is where this funny-looking guy named Avogadro comes to the rescue. Anyone remember this number? Avogadro's number, 6.022 times 10 to the 23 per mole. Now, how does Avogadro come to the rescue? Well, if we have 1 gram of tissue, of normal biological tissue, at least in a human being, we would imagine that about 60% of that tissue is water, maybe 20% of that tissue is fat, and about 20% of that tissue is invisible. Remember, protons, amino acids, phospholipids, other macromolecules are invisible. So 80% is visible, either water or fat. And it turns out that 1 gram of tissue, because of Avogadro's number, will have about 6 times 10 to the 22 visible protons. If only 3.4 per million are aligned, we're still left with 2 times 10 to the 17 protons that are aligned. So that's why we can see things on MRI, because even though the percentage that are aligned is teeny, 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 the overall number that's aligned is massive because of Avogadro's number. Okay, now the other thing that we should mention is that this net alignment is the same thing as M naught. And M naught is so M naught is the magnetic field that is induced in the body because of the fact that slightly more protons are lining up with than against the magnetic field. Now, M naught is very tiny compared to B0. So here's B0. Let's now see how big M naught is. So M naught is how big? There we go. There's M naught. Okay. So M naught is a teeny weeny little ant on the top or in the middle of Mount Everest. But little m naught is proportional to B0. So if you go from 1.5t to 3t, m naught doubles. If you go from 1.5t to 6t, m naught goes up by a factor of 4. Because m naught is what generates the signal, that's why the signal is proportional to the external magnetic field. Now the next question is, how are you going to see that? You want to see that little tiny m naught, which is surrounded, dwarfed by this huge B0. How are you going to see little m naught? Well, the way you're going to see it is you got to manipulate it. You got to manipulate it by getting it out of the same direction as B naught. So m naught can't be measured directly because it's too small. So to be measured, it must be flipped into the transverse plane. And for reasons that I'm not going to get into in too much detail, flipping it is going to require a radio frequency excitation. So here's m naught, and we want, I don't know how many of you can see this, but we want to flip little m naught into the xy plane. So here's B0, and m naught is the little, it's the skinny light blue arrow, and B0 is this big block arrow. But of course, B0 is much bigger than this, right? So let's expand B0. So we're going to expand B0 to be its real field strength to the point where it's completely, just completely usurping the field of view. So we have this huge B0 in the background, and now let's focus in on that light blue line, which is m naught. So in order to flip it into the xy plane, we are going to apply a radio frequency pulse. And that radio frequency pulse needs to be at the Larmor frequency in order for the, this m naught to actually experience it. Now, some of you will remember this from your high school days, that when you have a radio frequency pulse, that radio frequency pulse is associated with its own magnetic field. And this particular magnetic field is perpendicular to the external magnetic field. And we call the magnetic field associated with the radio frequency pulse, we call it B1. So B0 is the magnetic field associated with the magnet. B1 is the magnetic field associated with the radio frequency pulse. Now, what do magnetic dipole moments, as indicated by this blue arrow, do when they encounter a magnetic field? Well, remember, magnetic dipole moments will precess around B0, which is one magnetic field. What will they do when they encounter a new magnetic field, B1? Well, they will precess around B1. And that precession looks like this. So the precession around B1 is what tips it into the XY plane. So by applying a radio frequency pulse at the Larmor frequency, we cause hydrogen protons to tip into the XY plane. If we wanted to image fluorine, we would use a radio frequency pulse at the Larmor frequency of fluorine, and that would then tip fluorine into the XY plane. If we wanted to do imaging of sodium, we would use a different radio frequency and then tip sodium into the XY plane. But typically we're tipping protons from fat and water into the XY plane. So now that this is in the XY plane, remember B0 didn't go away. B0 is still pointing in the direction of Z. So now that it's tipped in the XY plane, it's going to keep precessing around Z like this. So we tipped it into the XY plane by precession around B1, but this thing is still going to be precessing around Z, and it looks like this. Now this is a little bit confusing. So now let's look at it down the barrel. So let's now look at the XY plane from above. And when we look at the XY plane from above, so you can imagine now that Z is pointing at us. So we're looking down the barrel of the external magnetic field onto the XY plane. And now we have our initial B0 is now tipped into the XY plane. And because it's in the XY plane, we're going to call it MXY. We're not going to call it M0. And this is now going to be precessing around the external magnetic field because things like to precess when they encounter magnetic fields. And what's the precession frequency? The precession frequency is equal to the external magnetic field times the gyromagnetic ratio of protons. So this will be precessing at 42.6 megahertz at 1 Tesla. You'll be precessing at 63 point something megahertz at 1.5 Tesla. So the precession looks like this. Oops, hold on. So now this, this MXY is precessing around the XY plane at the Larmor frequency. And if there was no such thing as dephasing, this would precess for an infinite amount of time at constant amplitude. But that assumption that there's no dephasing is incorrect. There is dephasing, and because there is dephasing, MXY loses amplitude over time. So this is, so I'll explain the dephasing in just a moment, but for now, what I want to emphasize here is that as it's precessing, it actually loses amplitude. So it doesn't maintain the same frequency, the same amplitude forever. And eventually it disappears and loses all of its amplitude. Now, why is that? Well, one of the things I did not make clear until now, and so hopefully I'll make it clear now, is that this MXY, which is that big light blue arrow, is created by the summation of all of the individual magnetic dipole moments. So I don't know if you can appreciate, but superimposed on the light blue arrow is a red arrow. And that red arrow is the summation of millions and millions and millions of individual magnetic dipole moments. These millions and millions of individual magnetic dipole moments are initially all pointing in the same direction, and therefore they induce this magnetic field by the light blue arrow in the same direction. So now let's see what happens over time. Over time, notice that these individual magnetic dipole moments start to lose coherence, they start to dephase, and as they lose coherence, as they start to go in different frequencies and they start to dephase, the net vector gets smaller and smaller and smaller. And as the net vector gets smaller and smaller and smaller, let me draw your attention here. Notice that as the amplitude gets smaller, the amplitude here is being graphically displayed as getting smaller and smaller and smaller. Now notice that this decay is an exponential decay, and notice that this decay looks a lot like that growth curve we showed earlier for T1, except that it's going in the other direction. So if growth is called T1, what might decline be called? Well, we can come up with a lot of things that might have been called, but it's called T2. So T2 is the signal loss due to the loss of amplitude due to the dephasing of the protons. So this is known as T2 relaxation, and T2 relaxation was also described by Felix Bloch, and it has this form over here, where the amplitude of the magnetization in the XY plane as a function of T is given by the initial magnetization at time 0 times e to the minus T over T2. So this looks a lot like the T1 equation, except the T1 equation had a 1 minus over here, and this one does not. Now, just like T1 can be described by a time constant in the denominator and a rate constant in the numerator, T2 can be described by a time constant in the denominator or by a rate constant in the numerator. So we have two equations which are mathematically equivalent to describe T2 relaxation. And just like with T1 relaxation, we're going 63% of from where we are to where we're going. It's the same thing over here. Here, we start out with a relative signal of 1, and after an infinite amount of time, we're going to get to 0. So after 1 T2 relaxation time, we're going to lose 63% of our signal. So if we lose 63% of our signal, we're going to go from 1 to 0.368. Once we're at 0.368, we're about 60. So now we're only 37% of the way to 0. What is 63% of 37%? Turns out that's about 23%, so we lose 23%, we get to 13.5, et cetera, et cetera. So let's look at it like this. So again, for T2 relaxation, we're going to be plotting the amplitude of MXY as a function of time, where time is represented by time constants. So 1, 2, 3, 4. And we're going to start over here at MXY0 for M0. And after one T2 relaxation time, we're going to lose 63% of our signal to there. We have 37% of the signal to go. After another T2 time point, we're going to lose 63% of what's left over, and we get to 86% signal loss, and we're down to 14. And then we're down to 5% signal, and then we're down to 2% signal, and after an infinite amount of time, we're down to 0% signal. So one of the things to notice about T2 relaxation is that as the time goes on, we lose more and more signal. And once we've gotten to 3 relaxation times, we've lost 95% of our signal. Once we've gotten to 4 relaxation times, we've lost 98% of our signal. Remember that for T1, it was the opposite, right? For T1, when we had 3 T1 times, we had gained 95% of our signal. And when we had 4 T1s, we had gained 98% of our signal. So T1 and T2 are sort of inverses of one another in a way. And just like with T1, different tissues have different T1 times, different tissues have different T2 times. And what I want you to memorize is that water has the longest T2. So water had the longest T1, water has the longest T2. Okay, now why do protons dephase? So I mentioned that if the protons did not dephase, if they all stayed at exactly the same precession frequency, we'd have no dephasing, there'd be no signal loss. But protons dephase. Why do protons dephase? Well, there's only one explanation for why protons can dephase. What is the frequency of precession? The frequency of precession is governed by the Larmor equation. The Larmor equation says the frequency is the gyromagnetic ratio times B0. The gyromagnetic ratio of every proton is the same. That's a quantum mechanical property. So every proton has the same gyromagnetic ratio. So therefore, there's only one possible explanation for why protons can dephase. Protons must experience a different magnetic field. So every proton has a slightly different magnetic field that they're experiencing, and because their precession frequency is proportional to the magnetic field, if every proton has a slightly different magnetic field, then they have slightly different precession frequencies. So let's go back to Joseph Larmor, and we remember that protons precess at the Larmor frequency. Let's skip this in the interest of time, and let me now explain what I'm talking about. So we start out with an external magnetic field, and now we have a proton. Now, here we have this $3 million beautiful homogeneous magnetic field. This magnetic field is so homogeneous. But now let's put a proton in there. This proton has a magnetic dipole moment, and this particular magnetic dipole moment is pointing up. So what is the magnetic field over here? The magnetic field over here is not B naught, right? The magnetic field over here is B naught plus a tiny amount of additional positive magnetic field induced by this magnetic dipole moment. So as soon as you put a proton into this beautiful homogeneous magnetic field, this beautiful magnetic field is no longer perfectly homogeneous. Now similarly, what if you have a proton that's pointing down? Well, if you have a proton that's pointing down, then the magnetic field again is not B0, it's B0 minus a little amount of magnetic field accounted for by this negative magnetic dipole moment. So as soon as you put protons into this beautiful magnetic field, it's no longer so beautiful. So let's imagine a perfectly homogeneous magnetic field illustrated by this gray slide background, and we take this one proton that has a positive spin to it, positive amplitude, and because it's positive, it's going to add to the magnetic field. So I'm going to put this sort of white cloud around it to indicate it's adding to the magnetic field. Now this proton is going to move around. And as it moves around, Everywhere it goes, it increases the magnetic field by just a little bit. What about this proton over here? Well, this proton is pointing down. It subtracts from the negative field, so that's why I'm putting this sort of gray cloud around it. And this proton also might move, and it moves in a random direction. And so everywhere it goes, it subtracts from the magnetic field. So this beautiful magnetic field that was once upon a time so homogeneous is now heterogeneous, not so homogeneous. Because it's not so homogeneous, depending on where protons are, they're going to be precessing at different rates. But now let's ask ourselves a question. This effect of the protons on the external magnetic field, what does it actually look like? Well, let's take water protons. These water protons are pointing up, and these water protons are pointing down. But do the water protons just sit there? No, the water protons are going to be moving, and they're going to be moving very, very fast. And just like a swarm of bees, they're going to be moving so fast that they're going to, just like a swarm of bees, they're just going to create this uniform buzz that's going to be adding and subtracting to it. Because it's such a uniform fast buzz, on average, they have very little effect on the external magnetic field. So water protons, pure water protons, that is pure water, relaxes very, very slowly because they're buzzing around so fast that they create a smear over the magnetic field. The magnetic field is actually fairly homogeneous. How about protons that are not in pure water, liquid water? How about protons that are in soft tissue, like the liver or the brain? Well, these protons aren't going to be buzzing around. They're going to be moving a little bit more slowly. So there's not this uniform buzz. These actually do affect the magnetic field and create heterogeneities that cause the protons to dephase. What about solid tissue like bone or cartilage? Well, now these protons are not even really moving. They're just sort of vibrating. And so they create tremendous heterogeneity. So water just creates this uniform buzz and does not alter the magnetic field that much. So water precesses slowly. At the other extreme, you have cortical bone where the protons are just vibrating and they create a lot of heterogeneity because they're not sort of randomly sort of canceling each other out. So bone relaxes very, very fast. A pure liquid water relaxes very slowly. If you had trouble following that, then maybe commit this to memory. Solid tissue like cortical bone has very slow molecular motion, very fast T2 relaxation. Liquid water has very fast molecular motion. It has very slow T2 relaxation. Okay, so this now brings us to the last topic for this first lecture, which is chemical shift. I mentioned earlier that protons experience different magnetic fields in part because the protons themselves alter the magnetic field. And because it's spins altering the magnetic field of other spins, I didn't make this clear before, that can sometimes be called spin-spin relaxation. So the spins, the protons, the magnetic dipole moments alter the magnetic field. They alter the magnetic field of other spins, so that's known as spin-spin relaxation. But there's another reason that protons have different magnetic fields, and that has to do with something called chemical shift. So chemical shift is the difference or the shift in the magnetic field that protons experience by virtue of being in a different chemical environment. So again, in MRI, we're usually looking at water and we're looking at fat. Water has two hydrogens attached to an oxygen. Fat, it's more complicated than this for today. Let's think of fat as a chain of carbons to which are attached hydrogens. This chemical environment is different than this chemical environment. And in what way is it different? Well, it's different in the following way. Oxygen is a very greedy nucleus. It is so greedy, it's very electronegative. It holds the electron cloud to itself. And because it holds the electron cloud to itself, it allows these protons to experience the full magnetic field. By comparison, carbon, C for communist, shares its electron cloud with these protons. And this electron cloud shields these protons from the magnetic field. Or in other words, these protons experience the full brunt of the external magnetic field, but these protons experience a lower magnetic field because they are shielded by the electron cloud that carbon is willing to share with them. So remember, the precession frequency is proportional to the magnetic field. That's the Larmor equation. So which protons will precess faster? These that experience B0, or these that experience something just a little bit less than B0? The answer is these will precess faster, and these will precess slower. So those precess very fast. These also precess very fast, but just a teeny weeny bit slower. What's the difference? Well, the difference is this. At 1.5 Tesla, the protons in fat precess at about 63 million hertz, and the protons in water precess at 63,217 hertz. So the difference is only 217 hertz, or only, and then at 3 Tesla, it's twice as much. So at 3 Tesla, the difference is about 434 hertz out of about 126 over 127 million hertz. So the difference is 3.5 parts per million. Not 3.5%, not 3.5 per thousand, 3.5 per million. It's a very, very tiny difference. But that tiny difference means that water protons and fat protons are not precessing at exactly the same frequency. And this has two different effects on MR. Let me illustrate the first one here, and then I'll review the second one. Remember I said before that in MRI, we are essentially imaging water and fat, but we are superimposing the two images. So we have a water image and a fat image superimposed. But in order to convert the signals of water and fat into an image, we have to apply a gradient in the so-called frequency encoding gradient. So we're going to apply a new magnetic field that's now going, in this particular case, from this side of the image to this side of the image. And the magnetic field is going to be a little bit higher here than here. Because the magnetic field is a little bit higher here, the protons will be precessing faster here than they will be here. But now here's my question for you. Will this gradient cause fat and water protons to shift by the same amount? And the answer is no, because remember, water protons precess faster than fat protons. So the water protons in this direction will now shift to the patient's right. And we end up with an artifact where in this particular case, on the patient's right, we have summation of water and fat, and on the patient's left, we have signal cancellation because one image got shifted relative to the other, and that's what accounts for chemical shift of the first kind. Now, in addition to chemical shift of the first kind, we have chemical shift of the second kind. And to illustrate that, I want to start by saying that we have water protons in blue and fat protons in yellow that are initially aligned with each other. And they're both precessing at about 63.8 million hertz. So they're precessing very, very fast, but the water protons are precessing just a little bit faster. So pay attention to the water protons and the fat protons as they precess, and pay attention to the signal that we get. So whenever fat and water are pointing in the same direction, they're adding up and we're going to get a high signal. Whenever fat and water are pointing in opposite directions, they cancel out and the signal goes down. So when water and fat precess, we'll see that they periodically go in phase and periodically go out of phase. When they go in phase, the signal is high. When they go out of phase, the signal is low. So we start with high signal because they're both pointing in the same direction, and let's see what happens. So as time goes on, notice that periodically water will catch up to fat, and periodically water will be out of phase, and then in phase, and then out of phase, and then we're in phase. And every time the water is out of phase with fat, we lose signal. Every time they're in phase, we gain signal. Out of phase, in phase, etc. Now, a question you might ask is, how often do the waters go out of phase, in phase, out of phase, in phase, out of phase, in phase with fat? Well, we can do a calculation and figure that out. At 1.5 Tesla, water and fat are out of phase at 2.3 milliseconds, in phase at 4.6, out of phase at 6.9, etc. At 3 Tesla, everything goes twice as fast. So at 3 Tesla, they're out of phase at 1.15, in phase at 2.3, out of phase at 3.45, etc. And here is an out of phase image and an in phase image. And remember that when fat and water are out of phase, we're going to see signal loss. And so let's look at these images. So this is an in phase image, and we see the liver over here. We see the spleen over here. This is a T1 weighted image. And I don't know if you recall, but remember that fat has the shortest T1 of any normal substance. So in a T1 weighted image, fat will look very, very bright. Something I didn't emphasize before is that the liver has also a fairly short T1. So the liver also will look bright on a T1 weighted image, but not as bright as the fat. So here we have liver, here we have fat. Spleen has a longer T1, so spleen is not as bright as liver. Spleen looks darker. Now we go to an out of phase image. The spleen doesn't contain any fat. So the spleen is it's a bag of water. So the spleen loses no signal when we go from in phase to out of phase. The fat is pure fat. So also the fat doesn't lose much signal because it's just fat. But what's happening to the liver? The liver loses signal because this particular liver is fatty, and we have the water protons and the fat protons on this out of phase image pointing in opposite directions. We have signal loss, so the liver loses signal on an out of phase image. Now, some of you might be noticing something else. You might be noticing that in addition to the liver losing signal, on the out of phase image, we have this very peculiar India ink artifact where we have this black line surrounding every water-based organ, such as the spleen or the liver, where these water-based organs interact or have a boundary with adipose tissue. So notice that muscle, water-based, India ink with fat. Liver, water-based, India ink with fat, etc., etc. What is causing that India ink artifact? Well, let's go back now to our image where we have water-based tissues such as liver and fat-based tissues such as adipose tissue. And remember that our MR images do not have infinitesimally small pixels. The pixels actually have a certain size as shown by this grid. So now what I want you to realize is that everywhere where we have an interface between water and fat, these pixels, like this one over here, contains water and fat. So we're going to have cancellation of signal everywhere that we have a boundary between water and fat. So those pixels go black, and that's what causes this India ink artifact. Okay, so let us summarize what we talked about. We talked today about a lot of things. We talked about how the fact that in MRI, we are operating in the electromagnetic spectrum. And in particular on MRI, we are operating somewhere between TV channel 2, which is 1.5 Tesla, and air traffic control, which is 3 Tesla. 1.5 Tesla is about 42.6 megahertz. 3 Tesla is about 127.8 or so megahertz, if I recall correctly. We talked about B0, which is this very strong external magnetic field that is created by a magnet. That this B0 is very important because it is the source, ultimately, of MR signal. It's also the source of MR artifacts. So 2 things are proportional to B0, among others: the signal-to-noise ratio and the artifact-to-noise ratio. In MRI, we are imaging protons, and we'll talk in another lecture coming up today why we're imaging protons, but we image protons. In particular, we image the protons in water, hydrogen protons. We image hydrogen protons, and not only, and we don't image all hydrogen protons, we image the hydrogen protons in water and fat. Protons have a quantum mechanical property called spin. This quantum mechanical property called spin induces a magnetic dipole moment. Any nucleus with an odd number of protons, neutrons, or both will have a net magnetic dipole moment associated with the nucleus. When we put protons in an external B0, the magnetic dipole moments of those spins will precess. Initially, half the magnetic dipole moments are aligned with, and half are aligned against the magnetic field, and there is no net magnetic field of these induced by these magnetic dipole moments. Eventually, however, and over time, more and more of the magnetic dipole moments align with than against the magnetic field, and after an infinite amount of time, a very tiny net number are lined up with as opposed to against the magnetic field, and that very tiny net lining up creates its own magnetic field known as M naught. M naught is what we're trying to image. That is the source of MR signal from, say, the human body, but M naught is very, very tiny. Now, in addition to the spins having magnetic dipole moments that line up with or against, these magnetic dipole moments will precess, and the precessional frequency is governed by the Larmor equation, which is the magnetic field the protons are experiencing times their gyromagnetic ratio. The rate at which we go from 0 magnetic field to M naught is known as T1 relaxation, and it's governed by a T1 relaxation time constant. Every T1, we get 63% closer from where we are to where we're going. After an infinite amount of time, we reach M naught. M naught is so tiny compared to B naught, we can't see it. In order to see it, we need to tip it into the XY plane. To tip it into the XY plane, we apply a radio frequency excitation at the Larmor frequency of the proton we're interested in seeing, which in clinical MRI in the year 2018 is usually hydrogen protons in water and fat. Once these protons get tipped into the XY plane, they will not even just once, even as they're being tipped, they continue to precess around B0 at the Larmor frequency, but because they experience different magnetic fields, they become incoherent, they dephase, and that dephasing results in T2 relaxation. During the lecture, I explained one mechanism of T2 relaxation, which is the fact that individual spins have their own magnetic fields, which can either be pointing up or down, and because those add up or subtract from the external magnetic field, they cause the external magnetic field to be heterogeneous. Water protons buzz around so fast, they create a smear that doesn't really create too much heterogeneity, but protons that are not moving so fast create more heterogeneity and dephase faster. And finally, there's another reason why protons precess at different rates, and it's called chemical shift, which is the difference in frequency attributable to the different chemical environment. Okay, well, we are done with lecture number 1.